Welcome to this month's GraalVM webcast series. My name is Steve Kwan. I lead product marketing for GraalVM, and today I'm joined by Ewan Slater. Ewan, can you introduce yourself a little bit?
Hi, my name's Ewan Slater. I'm Technical Director for the Java and GraalVM product marketing team. And I'm going to be talking to you today about some of the things you can do to shrink your Java containers and why you might want to do that.
Okay, thank you. In today's webcast, we're going to talk about how the GraalVM native image feature lets you create smaller and more efficient executables. Many of you know about GraalVM, but for some of you who are new to this topic, I just wanted to quickly give some context around GraalVM, and then I'll hand it over to Ewan. The GraalVM project is part of a large Java ecosystem. There's the OpenJDK on the left-hand side, which is really focused on the Java language. And GraalVM on the right-hand side is an optimized compiler. It's a project to build this optimized compiler. It's a big project focused on a couple things. So it's all about making the compiler faster. We're also helping compile Java down to native executables, which Ewan will talk about later on. Next slide. So let's take a look at how you can use GraalVM. There are a couple use cases, or three use cases. The first one uses GraalVM in the JIT mode to accelerate applications. The high performance compiler includes 60+ optimizations that aren't really in the default OpenJDK compiler to help applications run faster with no code change. In the middle is the second use case called the ahead of time compilation, designed to create native executables. This is a technology that helps microservices and containerized workloads. Ahead of time compilation compiles bytecode into a single binary. They're easy to deploy. They start without having to warm up, and it uses very little memory. And this type of optimization lets native executables help reduce operations cost. On the right-hand side is a third area called Polyglot. It lets organizations run non-JVM languages on the JVM. Developers can compile other languages down to a machine code like you can for Java. Being able to compile programs in other languages and being able to access their libraries helps make development teams much more productive. But today, Ewan will be talking about native image and shrinking the Java applications for container deployment. Handing over to you, Ewan.
Thank you very much, Steve. So I thought I'd start by giving you the takeaways from this session. So I hope what you come away with are the following key ideas. The first one is to make smaller things, is to improve our software by making small chunks of software rather than big ones. And when we do that, to only pack the things that we need. And when we've got just the things that we need that will make up this small piece of software, to put them in the smallest container that we can. Another key thing to remember is that immutability is your friend. Things that are immutable by definition don't change. There's no configuration drift. You don't have to worry about what that thing is now because it will be the same as it was the last time you ran it. To use multi-stage builds, Docker has this facility for doing multi-stage builds, and it's very flexible, and it really helps in building containers and making them small. And finally, that native images start faster and have a lower memory footprint than building a conventional jar file. So one of the best talks that I've ever seen was this talk that Sandy Metz gave at RailsConf a few years ago. And it's well worth checking out whether you are a Java developer or a Ruby developer or anything else, just for some great concepts. But one of the key things she said was that she's asked to comment on how people build better software. And she says it comes down to just one thing, really, one piece of advice. Make smaller things and let them know as little as possible about each other. And that is a really, really powerful thing to remember. So we've moved from trying to build big pieces of software that do everything to trying to build small, self-contained pieces of software, like an egg. If you think about an egg, and whether it's a chicken's egg in this case or a shark's egg, it contains all of the things that the creature inside needs to grow to the point that it's able to go out and survive in the real world. And really what we're doing when we build containers, when we put microservices into them, is creating that same thing, that self-contained piece of software in its own envelope with all of the things that it needs to go and operate and be independent. And then we can start to restructure how we build our applications and assemble them from these self-consistent bits of software. But they have a dependency on each other. They can work together, but they're not dependent on each other. And why does this matter? Well, because this vision is working. We can see from the recent CNCF Cloud Native survey that there is massive adoption of Kubernetes and container technologies as people across the industry are finding that this is a better way to build and run applications. And why is this? Well, I'm going to start with my journey. So 1989 was when I first got paid to write software, and I got given this textbook, a Fortran coloring book, and I had some time on the machine that you see there, or one like it, an old VAX. And I was working in a research lab, and we had a physical server, and it was shared. And this meant that we had configuration management issues. Different people would come in and change the configuration of the machine. We had version conflicts. Different people wanted different versions of the OS or different versions of a particular library. And these version conflicts could then become personal conflicts. Other people I've seen with the physical server world. There was a customer I worked with once who had a server build process that took 2 years to deliver a new version of a server. So you wanted that piece of software deployed. 2 years later, it would be in the standard server build and available for production. And also, there were capacity issues and conflicts. Everybody wants the machine at the same time. Nobody wants it at the hours of the day when it's free. So we managed to have a lot of contention on that resource and relatively poor utilization. Now, if you're rich in the physical server world, you could have your own dedicated server, but you've still got issues around configuration management. And now it's expensive. Yeah, you've got to go and buy that whole machine yourself, your department, your project, and the utilization on it is typically poor. It's not being used most of the time. Things got slightly better when we started to see widespread adoption of virtual machines. So we were able to partition the hardware. And you have different, same hardware is now supporting multiple virtual machines. And you've got isolation. You can have your own version of the operating system, or even different types of operating system on the same hardware. You choose the libraries that go into that virtual machine. You choose the application or applications that are on it. And it's portable. You can take that virtual machine, you can move it to a different server somewhere else. But it's heavyweight. If you've got 4 different virtual machines on a box, you've got 4 different versions of what might be the same operating system. So containers were a big step forward. Containers are lightweight. You don't have the guest operating system included. You also don't have configuration drift. Virtual machines still have that. You know, people go log in, they change things. Containers are immutable. When you start the container today, it's the same state as when it starts tomorrow. So it's repeatable. If you want a different behavior or different versions, you create a new container. They're disposable. Yes, if you've got a container that's running and you've done with it, or it's gone wrong, you get rid of it, you start a new one. And they're highly portable. You can easily take them from one environment to another, and you can rapidly deploy them and scale them in and scale them out. And you can also then start to put together a library or repository of your self-contained pieces of software as container images, and you can store them either on a public repository or in a private repository. So is everything perfect now? Not quite. There are still some problems with this vision. One of which is about size. As the Docker documentation itself says, one of the most challenging things about building images is keeping the size down. You know, it's really easy to go and grab Debian, for example, as an image. And that means that you pull a whole load of stuff in that you don't necessarily want. So as Joe Armstrong, the late, great Joe Armstrong, who came up with Erlang, said, you wanted a banana, but what you got was a gorilla holding the banana and the entire jungle that came with it. So you need to guard against pulling in stuff that you don't need. Because when we do that, we get bloated containers, and there's a number of issues with those. First and foremost is size. You know, you can easily give yourself a container that's more than a gig, and if you're trying to move that about quickly across networks, that's going to take time. It's going to slow you down. It's also going to have a bigger attack surface than you want. Yes, you've come with, say, the whole Linux user space in your container. That's a lot of things that somebody can try and attack. And there's also the question of vulnerabilities. If a bug is discovered in a library, and think about the Heartbleed example, you have to then go and rebuild every container that you have. You have to tear down the running containers, and then you have to rebuild every image that you have with that vulnerability in. So you want to have as few libraries in your images as possible, so that each image stands the least chance of being affected by a particular library having a problem with it. So only have the libraries in that your software requires, and that way you will do the minimum amount of tearing down, rebuilding, redeploying. So how do we combat bloat? We build the smallest image that we can. We use the smallest base image that we can find that's available. There's a number of small images that you can use, that you can base on. Building in an image is a good idea because, as I said before, containers are immutable. Yeah, in your image process, you run the build, it's always going to be the same. You have defined the development environment. You're not having to check, did somebody change something since the last time I ran the build? No, it will be the same as you have defined it in the Docker file. So building in an image is good for repeatability. And only pack the things you need. Only take your application, the things that it depends on, and the runtime that it uses. And if you can, go with ahead of time compilation, create a native image, boil that all down into a single executable, and then put that into the image. So what I want to walk you through here is an example, a demonstration of shrink wrapping a Micronaut application. So we're going to go through these stages. We're just going to create a Micronaut Hello World application. It doesn't really matter what it is. The first stage will just be a jar in a virtual machine. Then stage one, we're going to take that jar and we're going to put it in an open JDK image. So that's kind of an all-inclusive image. The second stage, we're going to build that jar inside the image. In the third stage, we're going to start to shrink things down. So we're going to create a minimal Java runtime environment with only the things that our jar requires to run. And in the stage 4, what we're going to do is we're going to use native image, part of GraalVM, to create that binary that will give us the smallest image and the quickest start and the lowest memory footprint. So I'm going to switch over to the terminal at this point. So that's just created as our Micronaut application. And if we cd into there, you'll see that we have the skeleton that is created for us. And if we do that, Micronaut run, it will build the application and it will run it for us. And we'll see that it comes up and it's running. Yeah. If we go in here, let's go back. And if we package that, yeah, so now we have our jar. Again, our Micronaut application running. So I want to then start the process of wrapping that up. So I have some Docker files that I created earlier. The first thing that we're going to do is just to put that Docker file, or put the shrink wrap jar into an image, and then we'll be able to run that. So, so that takes the image, that's put it into a Docker file, and we can run that. So that is so what we've done there is we've created our image, and then we're able to run that with Docker as a container. So the second stage, what we're actually going to do is we're going to make this build process immutable, because we're actually going to build in terms of the image. So we're going to start with OpenJDK as our base image. We're going to install Micronaut. Then we're going to create our application within that image. Then we're going to run the packaging there. And then we will have the jar file being run, but this is the jar file that's actually been created inside the image as it runs. So you could take that image and put it in a machine where there's no Java, no Micronaut installed, and it would be fine. So we run our build, we get that, and we should be able to. So again, that's running. So the third stage is where we actually want to start shrinking the image, because so far we've taken an open JDK image, we've installed Micronaut into it, we've done the build in there. So that's going to be, reasonably big. And what I'm doing in this case is I'm actually going from the image that we've just built, and so that as the jar builder, and then I'm going to use the capabilities, because this is an open, we've got the full open JDK there. I've got all the tools I want. So I need those tools at build time. I don't necessarily want them at production time. So we're going to use JDEPs and we're going to use JLink to build ourselves a minimal Java runtime environment. And then I'm going to copy that Java runtime environment to in this case, a Oracle Linux 8 Slim. So that's a skinny image, not much in it. So I'm going to copy the JR in, and then I'm going to copy the jar in, and then I'm going to run those. So this is using JDEPs to identify the dependencies that are in that jar file. And I'm using JLink to take those modules and add them together. So now we should be able to run that. Again, that starts up. So the final stage is to look at doing ahead of time compilation using GraalVM and the native image facility. So in this case, we're going to start with the actual GraalVM native image EE. That's our base image. We're going to start that as Graal compiler. We're going to go and get the shrink wrap jar that we built in stage 2. And then we're going to run the native image utility against that jar to create an executable called shrink wrap. And then again, we're going to take a slim Oracle Linux 8 image. We're going to copy the executable that we created in there. And then our entry point is just to run that executable. Okay, so you can see we've run native image utility against the shrink wrap jar. It's going to look at the classes, it's going to look at the different features, and it's run an iterative analysis process, an iterative points to analysis, where it goes and looks at the application, sets different starting conditions, and it runs through that process until it gets to the best result that it can get, and it can't improve it any further. And at that point, writes out the executable and, if you like, the starting positions of the different objects in memory. So having created that, we can then run stage 4. And you'll see that comes up in 15 milliseconds, whereas before it was taking close to a second to start up Micronaut. If we Control C out that, and stage 3 again. Yeah, so stage 3, close to 1,000 milliseconds. Stage 4, AOT, is orders of magnitude less. And then there's the question of the actual image size. So you can see stage 4 image is 177 meg. The stage 3 image, so this is with the minimal JRE and the jar file in it, that was 215 meg. The Oracle Linux Slim itself, you can see, is 110 meg. So in total, we added 67 meg with the ahead of time compilation and the native image. And then we've added 105 meg, slightly more if you were taking the minimal JRE route. The fattest image we actually created was the stage 2, which was where we had an end image, which was really a build image. So that was where we built, we installed Micronaut in the image, we built in the image, but we didn't then compress down and go to a separate runtime image. And the final one that we looked at, the initial one that we looked at rather, that was 485 meg, and that's starting with the OpenJDK image and just putting our JRE file into that. And so you see the OpenJDK image itself, it started at 471 megabytes, and the jar file that we've added onto that is therefore another 14 meg. So as you see, we've gone through the different stages of shrink wrapping this application, ranging from starting with the jar on a VM, just taking that jar and putting it into an all-inclusive image, building in the image and creating the minimal JRE. And at stages 3 and 4, we were able to significantly reduce the size of the image, and certainly in stage 4, decrease the startup time significantly, increase performance. So we've gone through a number of stages. We've come up with our self-contained, everything that the application needs to run, none of the things that it doesn't need to run. We have our little egg of an application. And so to revisit the takeaways, make smaller things. That's probably the biggest piece of advice. Make your software in the smallest chunks that you can and have them know as little about each other as possible. This is about building systems from small, loosely coupled components. When you're building those components, only pack what you need. Only take the dependencies that are necessary for your application to run. So that's in terms of like the build, you have things that you need at build time. If you don't need them at runtime, don't put them in to the runtime image. Put the image in the smallest container that you can. Make it as easy to move around as possible. Minimize the vulnerabilities that might come to you. Minimize your attack surface. Remember that immutability is your friend. things that are immutable don't change. They don't change underneath you. You don't have the concern that somebody's changed something in the build environment or in the production environment. An immutable image produces containers, and they all are all the same. They all start in the same way, in the same state. Using multi-stage builds allows you to have different build stages to copy things in, to use tooling from other images, and then to produce this lean, skinny image as a production image. And finally, native images start faster. If you can compile to a static binary ahead of time, that gives you a significantly faster start. It also gives you significantly better memory usage. If you want to learn more about Graal, here are some resources that you can look at. You can learn about Graal itself, and we also have some self-service labs. Steve, back to you.
Thank you, Ewan. That was a really interesting demo of how GraalVM generates these native executables that run more efficiently. If you want to learn more, Ewan has given you the resources that you can go to. And I'd like to open the floor now to take some questions and answers. Let's see, we don't have any questions on the board. Oh, here's one. Should I containerize all my Java workloads, and how would you prioritize them? Ewan, any thoughts?
I'm certainly not telling you to go and containerize all your Java workloads. The answer is, as usual, it depends. So containers are increasingly the standard way we deploy applications, but that doesn't mean that they're the only way. And I don't personally think that you should just change what you do because that's the current fashion. I had a colleague speak to me a couple of years ago and said, can we repackage my application as a set of microservices running in containers? I said, why? And he said, because the architecture looks a bit dated. It's like, does it work? Does it do everything it needs to do? Yep. Okay. And is there anything that you're being asked for by your customers that you can't do today with it? It's like, no. It's like, well, I wouldn't necessarily go through a lot of pain to deliver something that doesn't actually have any additional value. So I think it's really important, if you're going to containerize your applications, to understand the value that you're getting out of that. If it's part of a strategic initiative, you say we're going to put all of our workloads into containers because we think that that's going to give us a single set of management tools and that's going to make our life generally easier, then okay, but be aware that for some applications it might not be a great fit. If you've got something like a big monolithic app that's quite happy running in a VM or even on a physical server, then I personally would be inclined to leave that there unless you've got a good reason to move it. If you are moving workloads, if you are containerizing them, then I would start with the ones where you're going to get the most value. So typically those are the ones where you're going to have requirements around scalability or portability, or you need to improve utilization, because you don't want to have multiple copies of operating systems the way you do with virtual machines. If we're looking at new applications, I would start these days with a cloud native approach. I'd go that way first. And so typically you're going to be looking at building a set of microservices or a set of functions, and in which case containers is a good choice. And it's a good place to start.
Thank you, Ewan. Another question came in. How is GraalVM working to improve support in external dependencies?
GraalVM is itself an open source project. If you go and look at the actual open source project, you can see the work that people are doing. there's a lot of focus from the Graal team on extending Graal's capabilities to, use different sets of libraries. If you look at, so go back to Steve's point about polyglot. If you go and look at Graal, you'll see that one of the polyglot languages that's supported is Ruby. So we have Truffle Ruby, which is effectively Ruby running on top of Graal. And you can see there all the work that's been done to support the different libraries in the Ruby ecosystem. So now we're at the point where you can run Ruby on Rails on top of Truffle Ruby on top of GraalVM. And you can also, if you want to, do a party trick where you have Ruby code talking to Java code, and you can even have it talking to JavaScript code as well.
Another question that came in is, if you use a pre-built binary, won't you lose the capabilities of the JIT, knowing where to apply the most aggressive compilation based on the used expectation paths?
That's an interesting question. So yeah, one of the things that you see is where you've got native images, they will typically start faster. So they're more like sprinters. And then you have running on top of the JIT, it's more like, say, a long distance or a middle distance runner. So the sprinter starts fast at first, and then the other one overtakes it. So you've got that to a point, but also with GraalVM EE, that's the Enterprise Edition, we've got profile guided optimizations. So you can instrument the native image, and then you're able to take that output and feed that into, sort of an iterative compilation process. So now you can generate a native image, but with performance data from when it's running. So you're able to, match or even beat JIT even on a long running workload.
Thank you, Ewan. Let's see, I think that's all the questions we have. Do we have time for another one?
Yeah, I think so.
So let's see. Aside from making images small, what else can you do to make them more secure?
So you get into the area then of DevSecOps. So to make this concrete, I was working with a customer a couple of years ago, and well, the customer actually had an application that was monolithic. It ran on premises. They wanted to go into the SaaS business. And the first discussion, this is actually a really good use case. The first discussion we had with them was about scalability, because they found that now they were running in a cloud environment, different parts of their application were needing to be scaled out. And at that time, they were kind of having to scale out the whole VM just to scale out one component. So I worked with them. We refactored their application into a set of microservices, and each microservice ran in a container. So this is a case where there is value in doing this, therefore it's worth undertaking the engineering work to do it. So then we've got a set of microservices running in containers. And then one of their first prospective customers came to them and said, how are you ensuring the security of the container? At which point they were kind of, So one of the first things is, making sure that we avoid the bloat, because we minimize the number of potential vulnerabilities. Every piece of software is a potential vulnerability. You minimize the number of potential vulnerabilities in the container. But also then you start to go, actually, I don't want to be just pulling containers willy-nilly off Docker Hub. Obviously, it's better if you use the official containers, but you have a responsibility in your development process to vet those containers. So some containers you might get, say you decide when you go to get the official JDK container, or you decide to go and get the official container for your favorite Linux distribution. Then you need to vet those, you need to scan them for vulnerabilities, and I would suggest putting them into a private repository and signing them. And then you say to your developers, in your build processes, don't go and pull from the public internet, go and pull from this private repo where we've got images that we have assessed for their security risk, and they're signed, and then your developers create their subsequent images. They also get signed, get put into the repository, and then you only deploy your signed images that you've scanned for vulnerabilities that you know and trust. And this is part of your whole overall DevSecOps approach. And here, of course, automation is key, because you want all of those things to be happening automatically, that as soon as somebody's written an image and put it into the repository, something else is going to be coming along and scanning that and making sure that, as far as you know, it has no vulnerabilities before you put it into production.
Thank you very much.